Afternoon, good evening, wherever you are. My name is Arun Gupta. I am the Vice President and General Manager for Open Ecosystem at Intel. You can learn all about us at open.intel.com. Oh, right here, what it says. Or also watch a podcast where we talk all sorts of wonderful open source topics. Today, I am super excited to have June with me. Hi, June.
Hi, Arun. Hi, everyone. Thanks
Wonderful.
for inviting me.
So I'm really excited. It was a serendipity that I bumped into June. I've been involved with TED AI for last several months, and I realized June was one of the speakers. And I looked into the topic that he's working on, and I found it very intriguing, very, very futuristic. So hopefully, you folks will enjoy. I'm not going to spoil, and I'm not going to do justice to it. So I will let June do the introduction.
Fantastic. Hi, everyone. My name is Joon. I'm now a fourth-year Ph.D. student at Stanford in the computer science department. And I work around the idea of simulating human behavior. So you may have seen the Generative Agents demo. That's basically a kind of like game-like setting where if you play Sims, just imagine Sims, but NPCs are not just hard-coded, but they're actually dynamically generated. So they would talk and remember their interactions with one another, form relationships, and so forth. And more broadly, I'm excited about how we can use that ability to simulate human behavior to create various new applications, all the way from social simulations for testing social scientific theories, to building games, to building ubiquitous computing applications that require rich understanding of human cognitions. So that's what I've been up to. Yeah, and excited for today's conversation.
That's beautiful, actually. Simulating human behavior. Where?
Where? Right. So the context can really be anywhere, right? In the sense that the ability to simulate human behavior is a fairly general technique. So the setting in which we demonstrated this was actually, again, in a sort of a game world. So much like Sims, or the visuals are actually a little bit like Pokemon or Gather Town, if you've used that in the past, where the NPCs create a small town of themselves. So there's 25 NPCs that live together in a small town. They're everything that ranges from stores to schools, houses, apartments, cafe, bar, and so forth. And they walk around and they wake up in their houses, go out to buy food, get drinks together, even have a party together. So there's a Valentine's Day party that's going on in that town. So people actually gather, share invitations, actually come together to have the party, and so forth. And that's a setting. But I think really beyond that game town, you can sort of imagine the same technology being used. Let's say if you're a social scientist and you're about to run a social science studies or experiment, or if you're an economist and you're about to test out a new policy. Right now, those had to be done in real world on real people. And obviously, real people is sort of the best way for us to get the ground truth data. And that will never change because we have the ability to simulate. But there are many studies in which those ground truth data is just not available or too difficult to get. If you want to run an experiment that runs for such a long time on such a vast number of people, then most social scientists don't have the sort of the money or the time to run those kind of studies. Or if this is the type of policy that may impact millions of people, you do not want to test them on real people because it could be too dangerous to test new ideas just for the sake of trying it. So that's when something like simulating human behavior can come in, where we can stand in between the reality and sort of what is testable, sort of fictional world, where we try all these tests or validations in the simulation first, see how things might pan out, and then roll out in the real world. I think that's where we can offer a lot of opportunities. And sort of the last one I mentioned in there was ubiquitous computing applications. So imagine you have smart home devices or other computing applications that may help your usage in computing systems or any other ecosystem. A lot of these applications actually assume a deep and rich understanding of your behavior, patterns, cognition, and so forth. But a lot of those texts are actually quite rudimentary. So if you have any smart home yourself, you might already have noticed this, where a lot of the things that these applications can do is very much relying on the what if statement. If this happens, do this. But there's not a lot of higher level inferences that's going on. But if you can model human behavior, if these applications can be used, for instance, to model what you might need, then we can create those higher level inferences to more dynamically assist their users, change the environment, and so forth. So that's really the setting in which we're looking at.
Beautiful. In games, testing out economic theories, ubiquitous computing applications,
Mhm.
wherever we believe is more expensive to test on the human beings or try it out, that's where we are simulating human behavior. It may not be 100% close because it's simulation essentially, but you still get a good feel that, okay, is this idea worth pursuing in the real life? And that sort of becomes step one, and then you get into that.
That's right. That's right.
Beautiful. And that's your topic of research at Stanford. And what department? You're in the computer science department, or what is the department called?
I'm in the computer science department. So I'm a part, so within computer science department at Stanford, we sort of have different research groups. So I'm a part of SAIL, that's Stanford AI Lab. That's sort of the larger group that also encompasses smaller groups within it. So within it, there's NLP group, that's natural language processing group. And I'm also a part of human computer interaction group. That's a little bit adjacent to SAIL. But that's where we look at how we can really leverage new technology that's coming up to create new forms of interaction. All that to say, really, my research has to do with envisioning we have all this new cool technology. What are truly the new opportunities, interactive opportunities that we can create? So obviously, that new technology that I'm focusing on right now is large language model, foundation models. So really, what kind of interactions can we create with them? And my answer to that question has been, now we can simulate human behavior and fully general computational agents. And that could change a lot in terms of how we interact with computers and AI.
Beautiful. So your sister department is human computer interaction, but you are blurring the line right there, saying you don't need to have human computer interaction. In the computer, we can simulate a human itself. So that's a pretty novel concept. All right. So walk us through. I believe you have some slides that you want to share. Let's look at those slides and then we'll dig more deeper into it. I think this is very science fiction to me, honestly.
Right. So what would be sort of most helpful actually for this session? I usually actually, yeah, so what would be the most helpful? I actually do have some slides, some of which are just demo of the world that I have. Would that be a sort of an interesting place for us to go to?
Yeah. I mean, maybe walk through some slides, 5-10 minutes, and then dig into the demo part of it because we want to keep it very interactive. I would love see because you have been doing all this work out in the open source around generative agents. So I think what attendees would love to learn is what is the work that you're doing, show some real deal, and what are the ways they can contribute.
Yeah, that sounds good. Actually, if that's the case, if it's more of a 5 to 10 minute range, I'll actually use a bit of a cheat and actually use my I can share my slides from the TED talk that just happened.
Wonderful. Yeah, and that just happened Tuesday. So that's beautiful timing.
Yes. Let me see. So I'm not going to try to recite my memorized script because I'm now that I'm done with this, I don't. I'm trying to undo the memorized script part and go
Well,
back.
you don't have to memorize the script here. It's beautiful. I mean, TED has a really different appeal, but in this case, we don't need to. This is open source. Scrappy is perfectly fine.
Fantastic. Yeah, so instead of sort of me going through the entire slides, I think what I do is I can sort of share sort of the main visuals and videos within this slide. So I just skip around a little bit. Excuse me for doing that. But really, again, the idea here is to create what we call simulacra of human behavior. Simulacra actually has been an interesting term that we've been using, which sort of has similar adjacent meaning to simulation, but with some variation. But here we're basically saying we're going to create simulacra of human behavior. Let's see, various application spaces, behavior models, social robots, NPCs, social simulations. Really the space that I want to show you is, so this is sort of the initial demo. So this is sort of the individual agents within this world. So you actually see on the left, you actually see this is an old couple living in this town. You can see that they wake up in the morning, they're brushing their teeth and doing their morning routines together. And Jennifer, this is Jennifer, the wife, she's making breakfast and getting coffee. Sam is changing, and Jennifer is now reading newspaper. You actually see this behavior emerge within these agents. This is Isabella at the center. She's one of the main characters, sort of in this Smallville, is what we call it, where she's the cafe owner of Hobbs Cafe, and she's the one who's organizing a Valentine's Day party. So you'll see throughout the day her inviting her customers to the party, and even enlist help to decorate the cafe and actually host this party. So throughout the day, you'll actually see her buying supplies, also serving customers. So she usually hangs around at the cafe because she obviously has to interact with her customers throughout the working day. So it's actually quite interesting. And none of this behavior is hard-coded. So they just know that, okay, I'm the cafe owner, in which case I should really be at my cafe to host everyone. And on the right, you actually see this is a college student, Wolfgang, in this particular case. He's actually a student athlete. So this is set up in pretty early in the morning, all three panels. And you see him waking up, and he's pretty soon going to go off to do his morning run because he's a student athlete. So he wants to make sure that he's in shape. So he's now taking a shower. We should give him some privacy, but pretty soon he'll change and he'll go for a run. So that's what you're seeing here. Now, that entire individual behavior is now really gathered in this entire town setup. So you see all these agents living in this town. This is the full map of Smallville. You see 25 agents in it. And I showed you individuals agents just now, and you actually see them. So here at the top center, I'm not sure if you can see my cursor, is Isabella. So you actually see Isabella doing her routine there. Wolfgang is on the right-hand side. This is a small dorm, actually, they live in. Around here, you see Wolfgang there. And all the way on the left bottom, you actually see Jennifer, Sam. Sam actually is right now at the park taking a walk. So these agents are really just living their day. And really what's cool about this is not only are they deciding how to behave as individuals, but throughout the day, they'll actually talk to each other to share information, form relationships, and coordinate activities amongst themselves. So that's really the world that you're seeing called Smallville.
That is beautiful, actually. I mean, I'm starting to think, in terms of what kind. I mean, you said none of this behavior is hard coded. They know they are a cafe, like Isabella knows she's a cafe owner. So there are attributes that she is simulating being a cafe owner, throwing a party, what she needs to do. So I wonder what kind of information, metadata, what's the basis of this? Is there, you also mentioned foundation model, LLMs. So what's the back end of these kind of things? Because essentially what you're defining is, hey, here is an old couple. So what defines them to be old? Here is a cafe owner. What defines them to be cafe owner? Here is an athlete. What is the kind of metadata that is associated with each agent based upon which they act for who they need to be?
Right. So what's really cool is you can put in as much metadata as you want or as little as you want. And our system will generate these believable lives using whatever it has. So in this particular setting, it's actually quite straightforward. So this is the main architecture, which I'm happy to talk a little bit more about later. But really, to answer your question directly, the metadata that we have is actually quite straightforward. So this is one for Isabella. It's just one paragraph of description of who this agent is in English, right? So in this particular instance, we're describing Isabella. So she's the cafe owner of Hobbs Cafe, and she's organizing this Valentine's Day party. And we might have a few sentences about who she already knows. So if she already knows some customers, if she has friends, we mentioned that in this description. It really comes out to be just about a paragraph. And using just that, we're able to simulate their lives. What we're sort of assuming in the back end is really these large language models, and all these models or foundation models are actually trained on broad data that reflects our lives. So that includes traces from our social web, Wikipedia, and more. So they really encode a tremendous amount about how we live, the way we talk, live, and behave. So with even just this much of information, these models can generalize pretty nicely to generate these behaviors and simulate lives. So that's what we're really leveraging. I'm happy to actually, since we're on that topic, happy to talk a little bit more about how it's actually done.
So let me peel this a little bit. So you're saying for an agent,
Mhm.
you have their physical representation, which is
Yeah,
like the character or avatar that you're creating. In addition to that, you're putting this English text describing their attributes, and those attributes are then consumed by the underlying foundation LLM models, which are then they've been feeding on Wikipedia, kind of building that knowledge that is available on the internet. And based upon that, the fact this is a cafe owner, so the model knows what a cafe owner is supposed to do. And if a Valentine's Day party needs to be thrown at 5 p.m., so they probably backtrack from there that, okay, 5 p.m. the party needs to be done. So the invites need to go out. These are the friends. That's what she will invite. Is that sort of how it's perceived?
that's right. That's exactly right. So you can sort of imagine large language models basically being this micro cognitive modules. So actually, I think this might be a good time for us to briefly talk about this architecture.
Yeah, let's get into it.
So my general position in terms of how large language model based applications will develop in the future is everyone now has experience prompting and using these models in the form of ChatGPT or even GPT-4. Now, the way to me things are developed right now, where we just prompt these models and so forth, it feels very reminiscent of actually the early days of computing. So, go even all the way back to Turing machine and so forth, where really the idea there was to write new functions, new system. You're really wiring up all the backends. They're literally used to wires that you had to rewire and so forth. And that sort of showed the promise, early glimpse of what we can do with these new computing systems. But ultimately, what made these really complex behaviors using this computing power possible actually was higher level architecture, or today what we call operating systems or object oriented programming. These higher level design patterns or architecture that sits on top of underlying technology like computing bits and bytes that sort of put everything together in one unified concrete modules or architecture to make complex behavior possible. I think that's what we're going to see with large language model driven applications. So in this particular instance, what you're seeing here is basically this architecture where now this is the architecture of generative agents. And basically what you're seeing here is there's some perception and that gets stored in the long-term memory. And we retrieve certain parts from the long-term memory and generate plans, actions, and reflections. And really the core motivation here is to give that higher level architecture to large language models. And you can imagine basically each of these components having some form of large language model prompt that's really making this possible. So I'll give you some examples here. So really it starts from perception. This is the first step in this architecture. Our agents perceive things. So in the case of what Isabella perceived, you might see these characters. So this is Isabella here. She might see other characters talking to each other. There's a chair, empty chairs, and occupied chairs. There's somebody playing the piano. We translate all these perceptual stimuli into natural language sentences. So you see that on the right-hand side, Maria is chatting with Klaus, or the chair is empty. These are sentences that describe what Isabella actually perceived. And you can sort of reason why we're doing this. And we're doing this so that a large language model can think or can reason about basically the non-verbal perception. So in this case, these are, for instance, visual perception within the game world. So we're translating them into the form that a language model can reason or operate in. We store these in a long-term memory module. So this is what we call the memory stream. So
So
they
this
just,
is very similar to like how humans think. Like, I'm looking out the window, a dog is walking by, and that's what is stored in my head. So essentially, when you are simulating human behavior, that's what you're doing is just backed by LLM in terms of simulation now.
that's right, that's right. So in many ways, this is very much inspired by human cognition. So if you're sort of a fan of cognitive psychology or cognitive science more broadly, you may have noticed some of these patterns where we have this long-term and short-term memory. And going all the way back, in fact, AI actually came out, and human-computer interaction, both AI and human-computer interaction actually came out really of this department of cognitive science and psychology back in the 60s and 70s. Really, the founders of my fields were cognitive psychologists or scientists. So you're thinking about Alan Newell, Herbert Simon, all those folks. And they used to develop what we call cognitive architectures. And it's very reminiscent of those ideas, but just really reinterpreted or reimagined for the modern era where we have these large language models and much more complex agents that we can create with them now. So the memory stream, again, in this particular instance, is really playing the role of a long-term memory module. So everything gets stored here. And really the idea here is from this long-term memory module, we retrieve certain parts of it. And this is where our large language model really comes into action. So you may have all noticed the language model certainly has the context limitations. So language model cannot process one's entire lifetime experience because it's too much. And even if, and some language models actually nowadays have a much longer context window, but really the argument here is we need to make, as humans, as living beings, we have to make decisions at every split second, right? What, all the way from what to say to whether to react to a situation. And those are not something that you cannot basically reason about your entire lifetime every time you do that. And it's going to also output suboptimal behavior because many of those information that's going to be included are irrelevant to how we make decisions. So this is where really large language model comes in. So we first retrieve certain portions of this memory stream that's the most relevant to the current situation. So when we ask Isabella, what are you excited about? She's actually going to retrieve information that really might excite her. For instance, in this case, it's about Valentine's Day party, or right now we're talking about generative agents. So myself as an agent, I'm bringing out memory that I have about my work in this space. And we use that to generate plans, actions, and reflections for these agents.
So let's take a pause for a second.
Mhm.
You mentioned that today the way LLMs operate, like ChatGPT, for example, you
Yeah.
prompt and then they create an answer back to you. But the way you are explaining this architecture is now things are stored in the memory, like a long-term memory. So it's sort of auto prompting that, as a generative agent, as Isabella is moving around, she's thinking about what am I excited about. There is nobody prompting Isabella to think about it. It's just picking that information in terms of the English text, which is then backed by the LLM, and bringing that information to her. Is that a right summary?
That's right. More broadly speaking, there's also really interesting literature that's actually emerging around retrieval augmented language models. Really, the same insight that we're sharing here is in language models fantastic at this micro sort of cognitive, being basically this micro cognitive modules where given a narrowly defined situation, it's able to reason about or output any of plans, actions, reflections, summaries, and what have you. But it's not particularly good at maintaining a knowledge base and really being able to reason about them in a sort of with a long-term coherence. So really, we're creating an external database for these language models and retrieving only a select subset of that space to reason about what to do in the moment. And that's really the insight that we're using here.
Beautiful. One of the questions that is related here that I'm going to flash on the screen is it says that gets it back to agent driven programming to be more intelligent. Do you want to comment on that?
So I might need a little bit more context for this particular question, but the way I understand it, so I'm not sure if this is what the question is actually referring to, but certainly all the things, actions, reflections, and all these things that are being generated, they actually do get back into the memory stream. That's a broader point that I should make, where these agents basically have a self-perception. So everything they do, everything they think about, generate, they get fed back into their own system. And that ends up influencing their future behavior. That's actually quite an interesting capacity or sort of an important one where that's what creates their behavior to change over time. And we humans change our behaviors over time too. And you're basically imagining the agents doing the same thing. So they develop as basically agents over time.
Well, that's why it's a simulation of a human behavior. The more closer we are to human, the better it is. Okay, beautiful. Let's go back to your slide here then.
Yeah. So that's actually a summary of basically how agents work. Again, really the point I'm trying to make here, this is a high level architecture. So you can almost imagine this as a very early form of operating system that leverages basically a language model. And that's really one of the driving insight that we have here. So right now we've been seeing a lot of sort of large language model based architectures, or there's transformer architecture. Argument here is those architectures are going to be sort of the core ingredients, but we're going to put this together now as a higher level architecture to create these kind of systems. And human behavior, basically recreating a human agent, that's a complex behavior. And it's not an obvious one if you just have a large language model that these will be able to behave as a human-like agent. And that's really the bridge or the gap we're trying to bridge with this work. And really to drive the point home, in evaluation about the human likeness, the generative agents architecture that I'm actually proposing here produces behavior that is significantly more believable than ChatGPT, or even for that matter, GPT-4. You basically see 8 standard deviation difference in Cohen's D is sort of the metric that we have here. That's a significant difference between ChatGPT and these agents, and even more believable than human crowd workers role-playing as these agents. That is
Beautiful.
not to say these agents are more human-like than humans, because role-playing as somebody else is actually not an easy task for people, but it really is quite believable, or at least believable enough that a third person watching them behave actually think that this is more human than how we may have interpreted their behavior.
Got it.
That's really the space that we're in.
That's beautiful. Now you talked about Smallville. How big Smallville is, how many agents are floating around, and what's sort of the scale at which you have tested this?
Right. So really the scale that we have right now is this 25 agents. So this is the entire map. It's not a big map, but you actually see, let's see. So you see, I'd say all these small sort of rectangular things are sort of apartments there. There are some dorms and apartments, houses. So they're really looking at about, I don't know, maybe 10 households plus maybe 10 dorm apartment units. And then there are cafes and bars and stores and so forth. That's the setup. So 25 agents, not a big world. One sort of limiting factor technically here is the cost. These agents are quite expensive to run as they are right now. But of course, the cost is going down quite significantly as we speak.
That's wonderful. So there is a map is one part of it. Well, first of all, Smallville is quite indicative of what a real world would be, like a dorm and a house and a cafe and a park and you are a physical person, you are an old person. So it's kind of that diversity is there. So that's wonderful.
Right.
Let's talk a little bit about that cost element that you just mentioned, because end of the day, each agent is digging into an LLM because that's where their behavior is coming from. Have you done any cost analysis in terms of what does it take to run like a Smallville or or an agent or per agent cost, or is it a fixed cost? How does that model look like?
Right. So with 25 agents over 2 days, you're really looking at about $3,000 to $4,000 range. So that's the demo that we use in our paper, in our work. Now, the cost doesn't go up linearly as you add more agents because these agents interact, they talk to each other.
Right.
So to some extent, it does plateau. It's more of a sine curve, or it's sort of this, it grows up exponentially at first, and then it sort of tops up at some point. Because there's a limit to until you give them social media. In a physical space, there's a limit to how much they can interact. On social media, I'm sure it will go quite a bit higher. So that's what you're really looking at. To simulate one agent, certainly not might not be too expensive, especially if it's living alone. It's definitely not that expensive. With 25 agents living in this kind of town, what's actually quite interesting too is the cost distribution is not uniform across the time of day either. So at night, when almost everyone at least, is asleep, it's actually quite cheap and easy to run.
Right.
But during the lunch hour, when everyone gathers around, I'm not sure if you can see my cursor again, but this center top is where sort of there's all the cafes, bars, and things like that. That's when it gets really expensive because everyone gathers around there to get lunch and talk to each other. So there's a lot of interaction going on, a lot of reflection going on amongst themselves. So that's what we are really looking at.
Got it. So once you have built small will and you have created that infrastructure or a framework by which human behavior can be simulated,
Mhm.
is it mostly restricted by how intelligent your LLM is, or are there other elements that define that too?
Right. So the intelligence of large language model matters a lot because ultimately the underlying sort of again cognitive modules is really large language model.
Right.
So all the flaws and limitations of language models we do inherit. Now, that being said, what's actually quite interesting about this is to run believable simulation of human behavior, you don't actually need, in my opinion, GPT-10. Right? It does, I think, it does have a ceiling that in terms of its requirement. I think we can do a little bit better than GPT-4, but GPT-4 already can be quite powerful. My guess is by GPT, 5 or maybe not 5, but maybe 6 or 7, we basically have all the compute power and the reasoning capacity to create believable simulation of these agents. So after that point, it's really about the higher level architecture that we're going to create on top of them. The one that we created, that the architecture that I presented here, it's actually quite a simple one, but I do think it's a generalizable one because of its simplicity. And in the future, I can sort of imagine us trying to better implement each of its components. So we might try to create a better retrieval model or better planning modules and so forth. So that's what I'm expecting in the future.
That's wonderful, actually. And you mentioned $3,000 to $4,000 for running about 25 agents over 2 days. I would say that's a very low cost if it can simulate human behavior and you can experiment with elements of it. So that's wonderful, actually. Um, Let me bring another question here. Hope we can use this solution to solve mental health challenges using natural language processing model, interacting with real humans like a personal coach and psychiatrist. Thank you, Ashok, for asking that question. What do you
Right.
think?
Yeah, no, I think it's an interesting space. Um, Mental health is a very complex topic with a lot of sort of subtleties and nuances. But I do think one really interesting application spaces is to sort of allow users to talk to these agents um, and basically get whatever support they can get. Now, there's a limit to, I think, what agents will be able to play in the future, right? In the sense that these are not actually people. So I think it's important that the users always have a clear understanding that when they're talking to one of these agents, that they're talking to an agent and they don't form sort of inappropriate parasocial relationships. But I think there's a really broad space where even without going all the way to having parasocial relationships, the users can benefit by interacting with these agents. And mental health or these kind of health well-being in that sector, I think is a fascinating one.
That's beautiful. Um, as you were talking about LLM and foundation models, I want to dig into that a little bit more. But this is simulating human behavior. And one of the big discussions that has been happening over the last several months is sort of the ethical and the responsible element of it.
Yeah,
So, how do you make sure as you are simulating human behavior that those elements are incorporated into the model as well?
right. The first step obviously is to define sort of what. So this ethical issue, I think, is key to make sure that these agents actually have, become an empowering aspect of technology and not something that sort of replaces what we already have between humans. And I think that's a really important part to get right. The first step, of course, in there is to create the societal norms around what we want these agents to do, right? And then there's the task of implementing that vision. Now, in terms of what we want them to do, for me, again, I think these agents are incredible proxies for human behavior. So they can really help us better understand ourselves in many situations when we cannot do direct observation or engagement with people. That's where I see the opportunities. The places where to me, I'm a little bit uncertain about is when, again, we're creating these agents to actually advocate for parasocial relationships, or even worse, sort of the thing that that I fear the most is these agents actually forming a parasocial relationship with a user and then sharing or misinformation or persuading them to behave in certain ways. That might not be sort of for the user. And you can sort of immediately see why this could be really dangerous, right? It's one thing for some random person to tell me on social media that X is true, but if my friend, my closest friend that I trust tells me X is true, that has a different meaning. And that's what I'm sort of the most afraid about of in this space. So I think really forming the right guardrails around those kind of use cases, I think is going to be critical. There are a few ways to do it. And I think I think this is something that we will have to work on in the future as well to come up with more ideas. But one instance here is really dedicated audits of these systems. So audit basically has to do with keeping a record, oftentimes by a third party, of sort of all the underlying behavior that is being sent out using these models. So, right now a lot of models are centrally hosted. To in the sort of for the audit purposes, that actually could be a benefit because we can centrally audit, let's say, the models that underlies all these behaviors and cut them from the source when these agents or models are misbehaving or conducting these sort of persuasive or parasocial relationships with users. So that's certainly one approach. Another one obviously has to do with more fine-tuning or making sure that model itself understands that when it's trying to get involved in these kind of behaviors, it knows that and it sort of stops doing that at the moment of generation. So I think those are some of the methods that we have available right now. Some of those I think are being implemented as we speak. But I think the space is actually quite broad, and I think there will be a lot of other techniques that will come in the future.
Absolutely. I think there is definitely, as you said, those elements super important, and it's a early stage. Guardrails are being put, and it's a matter of time, where it becomes more clear on what that needs to look like.
Yeah.
The last question before I want to see some real code as well. What do you think is the relevance of these models, like foundation models, LLMs, to be open? And what does open really mean? Does it mean open source, open data, open code, open weights,
Right.
open model? What does open mean? Well, first question is, what is the relevance of open in this case? And second is, what does open mean?
Yeah. Right. So I think there's a lot of debate, obviously, in terms of. I sort of start with the latter because I think it's maybe a little bit easier to enter from there. Of course, with these models, there's a lot of debate in terms of what does it even mean to be open. Like, do we just release certainly we can access the API, but for OpenAI model, but that doesn't feel quite open. Do we actually want all the weights? Do we even want the training data of these models so that we can train them from scratch? So I think to some extent, I think the unsatisfying answer here is everything sort of lies on a spectrum. And as we have more open source models, there's more things that we can do and more attacks for angles too. So I think there's no sort of one size fits all model to doing this. But to some extent, obviously, my advisor is Percy Liang. He's one of my co-advisors who's been really advocating for these open source models. And I buy into his vision that the more open these models are, the more we as researchers and as a community can do to understand their impact, what they're doing, and really developing them to align it with our values. So I think that's sort of the space that we're in. Um, I do think for the moment, though, there's a lot of sort of fog of war to some extent, where I don't think the dust has sort of settled in terms of where we're going to go, and I'm sure there's the market interest as well. And I think we as a community sort of have both the right and duty to fight against the market interest in cases where we think it doesn't serve sort of the broader interest of our society. But those are always not the easiest conversation to have or the straightforward
I
forward.
agree. I agree. Very well put. And as you said rightly, it's a spectrum. API, weights, data. The more open it is, the more people are able to believe into it because then they know how it is trained and what's the weight, and I can retrain the model if I need to. So I think that's really right. And as you said, I there is no one right answer. And what is it and how is it? And you mentioned Dr. Percy Liang. I just saw his white paper that got released like yesterday or a day ago, a couple of days ago. Foundation Model Transparency Index.
Mhm. I think we may have gotten disconnected.
And they have taken like lots of different ways by way how there was a Foundation Model Transparency Index report that was released by Dr. Percy Liang and a bunch of other folks as well.
Mhm.
I was reading part of it, really fascinating. Models are what they are, but just being aware of where do they stand in the spectrum is important element.
Right.
All right, June. So I would love to see some code. I know you have a GitHub repo.
I
What can
do.
you do it live?
Right. Let me see. I haven't really done this in the past, so it's going to be fun venture to try to show this to everyone. So let me just do screen share again here. Okay. So this is the repo. I'll be upfront about it. I haven't really done a good job maintaining it. Like some other public repository, I think it's more of a. This is something that academics sometimes do, where we have a paper, we sort of release all the code, but we don't actively maintain this as a package. So really, the goal here is to share with the community how the original generative agents were made. But I think really a lot of the details are quite specific to sort of the game world that you saw. So a lot of the code is about grounding agents in this game world and so forth. So there might be much lighter weight code bases that you can use if you actually want to create your own agents. But I can briefly show you what this is doing.
So
So
you're saying not well maintained yet. There are 13,000 stars to the repo.
yes, actually, I think most of those stars came during the first week. So I think in 7 days, I think it was sort of the fastest growing
Yeah,
repo.
people apparently like something about it. A lot about this. So yeah, I would love to see more.
Yeah, but I think the side note there is I think the growth has sort of because I wasn't maintaining it. I think sort of the interest sort of came in at first.
I understand. Yeah.
So I think that's sort of where we are.
Yeah.
But again, really, this is just to show you how it was done, and it's not really meant to be maybe used for particular other applications beyond these games, but it's really to inspire. So you can you can run your own simulation. I think that's certainly the fun part. So everything is included. So there's just a to-do here or sort of a how-to readme. So setting up the environment all the way from, I think I won't go through sort of all of this because I think it's just, you can just take a look and see what's in there. But ultimately what it promises is you can replay any of the simulations, but you can also create your own simulation. You can even author some of your own agents, so you can customize it to some extent. So that's what we.
And for this purpose, what is the LLM? Are you using ChatGPT backend, OpenAI backend? What are you using?
That's right. We're using ChatGPT. You could use GPT-4 now. And really the place to touch is actually in this file, utils.py. Maybe not, actually. There are a few files, if you read into it, that you might have to touch, but this is where you put in sort of your API key, and there's a function in there that I'm happy to show you right now, where that is, that you can change the models and so forth. You might actually have to change the prompt a little bit to make that happen. But that's the sort of this repo. I actually talk about the repo a little bit. Again, I've never sort of talked about this repo live, so apologies as I sort of work my way through here. It sort of has two parts. One is the backend server, and the other is the front-end server. Backend server is where all the agents, reasoning, and all that is happening. All the actual cognitive simulations happening. And front end is what's rendering, what's grounding the cognitive processes into a map, a game world that you can see. So let's take a look at here. So Reverie is sort of the main backend server. So if you go in, and this is actually where you'll see all the prompts as well. So the backend server in there. So there are some global methods. Maze. Maze is basically what defines all the, what's the best way to put it? Sort of the map information. So you actually see all the functions that are related to,
That is the actual Smallville representation that we saw. It kind of is a programmatic representation of that.
That's right. And, you know, it's the development of the game world is actually fairly, we follow the common practices. So it's a blocks world, or it basically, or not blocks world. It basically is, you know, bit by bit description of where things are. So this particular pixel has, let's say, a kitchen in somebody's house, and it has that definition. So you'll see all that getting defined here. I'm happy to look at some of the assets file later, but that's the main, there's some Pathfinder. Reverie.py actually is the main function that puts everything together in many ways. So you actually see this is the main function that you'll end up writing. This is the server function. You can set up a lot of the, and you can actually, the main way of interacting with this particular file actually is by command line interface. So you can actually run the tester server, exit, save the simulations, and actually inspect or even talk to the agents. This is where you would do it. So you can actually print some details about each of the agents. You may notice that we actually use a older naming convention. So we used to call these agents personas. So that's persona basically means agents in this space. If you go down, there's actually a way to call these agents as well. So there's call analysis, and the agents will talk back to you and so forth. So that's what you're seeing here. That's Reverie. That's the main test. That's main backend server. Now, this I think is going to be the part that would interest most of our our viewers. In the backend server, there is this, again, persona stands for agents here. This agent folder is where all the cognitive modules of these agents are defined. So everything is put together by this persona.py. So you actually see that here. But really, I think what you should be looking at is the cognitive modules and prompt templates and memory structures. So cognitive module defines how we are going to basically create plans, reflections, and execute this is actions.
So this goes back to the original diagram that you showed, plan, act, retrieve, memory, all of that.
That's right. That's right. These are exactly the modules that they map to those individual modules here. This is how they're defined. So if you actually look at plans, you basically see all the functions that are being used to generate these plans. And all the generate functions basically means individually they're calling ChatGPT. So you actually see the run prompt functions being called for each of these generate prompts or functions. The only one extra one that we do have actually is converse. This is actually for generating dialogues or socialization module. That wasn't in the architecture, but it's very much part of that execution and planning module. So this is how individual sort of modules are defined here. And you actually see the memory structures. So scratch memory that's the retrieve short-term memory. So you actually see, and it actually has some other things, some states that we have for the agents, their current location, some hyperparameters that you can set, like how far into sort of the map they can see, some other hyperparameters, their traits, their names, and those are getting maintained here. But this again is sort of their short-term memory. And then we have what we call the long-term memory module. And this is the memory stream. So again, we sort of use an older naming convention. We used to call the memory associative memory. We originally actually designed this as knowledge graph, which we didn't end up using, but that's where sort of the name convention comes from here. And it's composed of concept nodes, which is individual memory records. So you actually see sort of the timestamp, like when it was created, when it was last accessed, the type of memory it is a reflection, thought, event, chat. So that's what you're seeing here.
Got it.
One thing that I mentioned is sort of interesting is the spatial memory is not really something that was in the architecture diagram, because I think it's a little bit adjacent to other types of memory. But the spatial memory is actually what grounds these agents in this map. So the way we represent, because again, the world is in physical space, at least in 2D physical space, but these agents operate in natural language. So we need a way to bridge those two. The way we do it is we basically represent this world in a tree, in a really large spatial tree. It's a simpler version of scene graph is sort of the best way you can imagine this, where the nodes are locations and the edges basically represent containment relationship. So in my apartment, there is a kitchen, bathroom, and so forth. So at the top of the node, it might have a node for my apartment, and then edge coming out of it that directs to kitchen, bathroom,
Right.
common area.
Right.
And these agents individually encode a subset of the tree that they have already seen. And they wouldn't know the places they haven't, but it basically maintains a part of the tree, the global tree for the space. And the agents maintain the subset. And what they do is that they then use a language model to traverse through that tree. So imagine that I want to cook. Where should I go? Well, I'm in my apartment. There is kitchen, common area, bathroom. Where should I go? It's a classification problem that language model can do.
Right.
I would go to kitchen, for instance. That's what the spatial memory is doing here.
Gotcha.
So it's just a few recursive functions or something like that that basically maps, makes that happen.
Yeah. What I'm realizing is I'm looking through the source code files here as you're walking them through.
Yeah.
For simulating human behavior, I mean, it's a lot of code, but for simulating human behavior, this is not bad at all. I mean, this is like in a very little amount of efficient code is where you've been able to create that model, and now somebody can just pick it up and run with it.
I agree. I think that's really the beauty of it, because in the early days of cognitive architectures and early days of MPCs, you really had to write behavior trees for these. And to create a behavior tree for something as complex as human behavior, that's not one person job.
No, not at all. At all. And that's exactly where we are relying upon LLMs. So mostly what you're doing is you're relying upon ChatGPT for bringing that information in. And then all you're doing is just weaving the pieces together so that it can give you that unified interface where they're able to move around. And for a behavior, you take that English description that you explained, oh, Isabella, coffee owner, Valentine Day party, feed it to the LLM, bring it back, and then just enact it out.
That's exactly right. So that's really what you're seeing here. Yeah. And I sort of really quickly mention prompt template. This is where all the prompts are for generative agents. I believe it's the version 3 ChatGPT one that we use for our paper. So if you go here, you'll see all the prompts. And the prompts, I sort of have created when I was creating was sort of before the days of LangChain. So I basically created my own version of basically LangChain here as a part of all this packet. So you'll see the prompts and what's getting replaced. These are just comments at the top. So for individual prompts, you'll see that. And you'll see different versions that I tried for some of this. So you can see that planning clearly had a lot of iteration
Right.
to get that right. And
So what you're saying is, instead of doing this, if you were to, you would probably use LangChain now.
yeah, I think LangChain works quite well. And they also implemented some part of generative agents too. So if you want to try something without writing much code, I think that's an obvious option that you can sort of take.
Wonderful, because I'm actually bringing Harrison Chase here in a couple of weeks
Nice.
to talk about LangChain and the power. So I'll make sure I mention that question about generative agents.
Yeah, Harrison's fantastic. And I love all the work they're doing over there at LangChain. So I think it's fantastic. And for here for now, this is sort of what you're seeing. Yeah, is there anything that I should mention? I mean, that sort of is it. Again, if you go all the way back to the top, this is the environment file. This is where all the map is getting developed. This is a Django package. So there's a Django server running that connects everything. This is where we also store the simulation data. So you actually see the simulations getting stored here so that you can rerun it later.
That's wonderful.
Yeah.
That's wonderful.
That sort of covers everything.
My God, this is amazing, actually. Very science fiction, honestly. And as I said in the beginning, I'm really thrilled that we are able to get into this conversation and talk about generative agents. I think today we covered a lot of ground around what simulacra is, what does simulating human behavior mean, how we are leveraging LLM foundation models as the back-end infrastructure for the actual human behavior part of it, and how we are weaving all of that together over here. We talked about the spectrum of openness around foundation models. We talked about the ethical and the responsible elements of it. We touched upon the cost aspect of it. We talked about the economist, computing apps, building games, the usage of it. Beautiful. I mean, it's such a vast topic. Anything else? I know we have just about a couple of minutes. Joon, anything else that you would like to say here?
Let's see. No, I think that actually is a lot that we covered today. I think the application space for something like, simulating human behavior is quite large. And really, it's up to the imagination of the users and developers who's going to come from now on to really make use of this. And maybe one last thing I sort of mentioned here is I think there's such a big opportunity space. And I think that was one of the main themes running through at TED AI as well, where, again, the space of possibility and opportunities is so big that I think we can really pick applications that we know will empower people. And we can just focus on that, and there's going to be a lot of value that's going to come out of it. So I'm really excited to see what people will build on top of this, and looking forward to what we find.
I think you're absolutely right. And, I'm a runner, so my analogy, the way I think about this is, are we even at the launch line? Are we even at the start line? Because once we are at the start line, the possibilities are endless in that sense. So yeah, no, I completely agree. I really hope people get inspired by this generative agents document, paper, and all the wonderful stuff that is happening, and pay attention to it. Joon, thank you so much. I really enjoyed the conversation today.
Same here. Thank you for having me.
Absolutely. Take care. I'm going to end the stream now.
Fantastic.